For this experiment, we wanted to find the different moments of inertia between different disks when they roll down a ramp created by a shoe box and a wooden plank. So first, we created these disks with Bristol paper cut into a circle with a rim around it. And then we created 3 of those with the same size and dimensions. And then we added 6 paper clips to each side of the disc so that the masses of the 3 discs would all be the same, but the distributions of the paper clips would be different around the center of rotation. So for example, one of them had paper clips all around the edge spread out at equal lengths. The other one had all the paper clips centered at the center of rotation, and then the third one had 2 clumps of 3 paper clips on either side. With this, we predicted the disc with the paper clips centered at the axis of rotation to have the least amount of moment of inertia and therefore have the greatest angular velocity at the end of the ramp because the masses are centered at the center of rotation. And then we also predicted the disc with clumped paper clips at either side, as well as the disc with the paper clips around the edge to have the same moment of inertia because those paper clips are all equidistant from the center.
So we chose to attack the situation via the energy lens, and so we note firstly that we start with gravitational potential energy, and that is converted to kinetic energy of both the rotational and linear kind. And so let's draw a picture to begin with. So we have this ramp, we have the height of the shoebox represented by the h, and we have this distance x between the shoebox and the end of the ramp. And here's our disk. We have the masking tape in the center, and this is what we're tracking using Tracker. So firstly, Tracker gave us data in terms of some displacement x and some displacement y, and we wanted to find the displacement in terms of this parallel displacement d. And so in order to do that, we needed to find this theta, which is equivalent to this theta. So in order to find this theta, we did some trigonometry, meaning tangent theta is equal to h over x. And from that, we found theta is equal to the arctan of h over x. You know, we haven't done trigonometry yet, but it's necessary in this scenario. And then we found d using cosine theta is equal to x over d in this triangle up here. And so using that, we were able to find that d is equal to x over cosine theta. And using that, we were able to find the displacement as a relation of time, and then taking the derivative of that, we found the velocity as it relates to time for each of these disks. And then using the equation omega is equal to v over r, we were able to find the angular velocity as it relates to time for each of the disks. So going back to this initial equation, once we had the angular velocity as it relates to time for each of the disks, we have that potential energy is equal to mgh. We have linear kinetic energy is equal to 1/2 mv squared, and we have this rotational kinetic energy is equal to 1/2 I omega squared. And so what we were looking for initially was, is this experiment, does it work in order to find this I? And so by finding the initial mgh, which should have been the same for all of the disks, finding the final kinetic energy using our data for each disk, and then subtracting those in order to find the rotational kinetic energy and solving for I, we were able to deduce the I's for each of these disks, which we will show you now.
As you can see in the graph, the angular velocity at the end for the disk with the paper clip centered at the axis of rotation had the greatest angular velocity, meaning that they had the least amount of moment of inertia. And this aligned with our prediction. But then the disk with the paper clips spread around the edge of the circle was found to have less moment of inertia than the disc with the paper clips clumped up on either edge, which did not align with our prediction. Some possible sources of error for this experiment was found to be having to glue the paper clips onto the disc and tape as well, which added weight to each object, so each of the discs may have had slightly different masses. And then Tracker also had some errors as well when measuring the spaces between points, and I had to manually click on the center of rotation for some of the points, which could have caused a little bit of error in the graphs.